an important property of cross products. This is something that you can explore in your homework. V crossed with W is not equal to W crossed with V. What? It's sort of like multiplication. You want it to be like multiplication. With multiplication, you can flip-flop the order and it doesn't matter. It turns out when I take this determinant, the order will matter. And in this case, we see that V crossed with W is always going to be equal to the negative of W crossed with V. It's another thing. Another aspect is that this resulting vector, the cross product vector, V crossed with W, is orthogonal to V and to W. What does orthogonal mean? Orthogonal is just the three-dimensional analog of perpendicular. So if two vectors are orthogonal to one another, it means that whatever plane that they live in, they are at right angles to one another. We use the word orthogonal because perpendicular we typically refer to when you're stuck on a plane and it's really obvious what plane it is that that right angle is formed within. And the final piece of geometry that's important to note is that cross products follow what we call the right-hand rule. So what do I mean by the right-hand rule? They follow the right-hand rule. Well, to take an example, let's check out what happens when we cross the vector I with the vector j. So when I say the vector I, I'm thinking of the vector 1, 0, 0, and I'm crossing that with the vector 0, 1, 0. I'm going to do that really quickly by hand, looking at my matrix, I, j, k along the first row, 1, 0, 0 along the second row, and 0, 1, 0 along the third row. We're going to get a lot of zeros in here, so it's going to go really quickly. I times the determinant of 0 times 0 is 0. J times the determinant of 0 minus 0 is also 0. Plus k times the determinant of 1 minus 0 is 1. So I just found out that when I take I crossed with j, I get k, which is the vector 0, 0, 1. And if I look at the geometry of these vectors, think of this in terms of my xyz plane. My I vector is the vector right here. My j vector is the vector right here. And my k vector is the vector up here. The right-hand rule is telling me that if I start with the I vector and then move to the j vector, the resulting vector of that cross product gives me something that's normal to the first two. It's perpendicular to both I and j. There's this perpendicular right angle right here. There's this perpendicular right angle right here. And it's pointing in this positive direction. If I would have taken the cross product in the other order, you can flip this almost in your head. You can see that if I take j crossed with I, that's a really funny j. There we go. J crossed with I would have gotten negative k, meaning that if I start with this vector and then roll to the other vector, starting with j and moving to I, my resulting cross product vector would be pointing down in this direction, which is exactly in the negative k direction. There's one more property that's important to note about cross products, and this is the one that's easy to get confused with dot products. It turns out that V crossed with W, if I want to know the magnitude of this, it's going to be equal to the magnitude of V times the magnitude of W times the sine of the angle between them. Notice it's important to put magnitude vectors here. This right side of the equation, the magnitude of V is a real number, the magnitude of W is a real number, the sine of an angle is a real number, so this is just some real number. If I didn't have these here, I would be saying that a vector was equal to a real number. Doesn't make sense. So we know that this is a theorem. I'm not going to prove this theorem, but the theorem says that the magnitude of a cross product is equal to the magnitude of each of the vectors times the sine of the angle between them. And given that piece, we're going to finish with an application of cross products to finding areas. So I want to know, what is the area of the parallelogram spanned by a vector v and a vector w? Well, this is something that I think is really cool. First you have to ask, well, what does it mean to be a parallelogram spanned by vectors? I think that it's important to look at what the geometry is. Let's say that my vector w is a vector that looks like this, and my vector v is a vector that looks like this. I'm going to put them so that they have the same point of origin. And this doesn't yet look like a parallelogram. So a parallelogram spanned by these vectors is going to be the object wherein I put on another copy of v down here, and then I put another copy of w up here. And that's my parallelogram. This is the parallelogram spanned by v and w. If I want to know the area, the area of a parallelogram, this is something that maybe it's been a while since you've thought about finding areas of parallelograms. And the way that this is drawn, it might be hard to think about also. I'm going to take this parallelogram and rotate it a little bit, just so visually the rest of my picture is going to work out and look a little better. So now that I've rotated it, you might recall that when finding areas of parallelograms, the area of a parallelogram is actually just given by the base times the height. So the length of the base, which in this case, if I let w be the length of the base, it's going to be the magnitude of w times the height. And what do I mean by height in this case? Height has to be exactly perpendicular to the height. So I want to know, essentially, I'm asking, how tall is this? It's not the length of v, because it's tilted a little bit. I want to know exactly what the height is, so that the height that's exactly perpendicular to my base vector, which I assigned to be w in this case. It turns out that just from geometry, we can figure out what this is. This is a right triangle. I'm going to label the angle between v and w as theta, which is common. And so I want to know, what is this height? Well, using triangle geometry, we know that the sine of this angle is going to be the height divided by the magnitude of the hypotenuse. So in this case, the sine of theta is equal to this height divided by the magnitude of the hypotenuse. And in this case, the hypotenuse is the magnitude of v. So I just found out that the sine of theta is the height over the hypotenuse, the magnitude of the hypotenuse, I guess. So if I'm solving for height, in this case, my height is going to be exactly equal to the magnitude of v times the sine of theta. Well, this is where our great application of cross products comes in, because we just talked about how we can compute the sine of theta. We just decided that the magnitude of the cross product is equal to the sine of theta times the magnitude of each of the individual pieces. Or, if I rewrite that, I'm saying that this sine is exactly equal to, maybe I'll have a think bubble. What am I thinking off to myself? I'm thinking off to myself that we know that the magnitude of the cross product, oh, you might not be able to see this ink on the camera. We know that the magnitude of the cross product is exactly equal to the magnitude of each of the pieces times the sine of the angle between them. And if I solve for the sine of the angle between them, it means that the magnitude of the cross product divided by each of the individual magnitudes multiplied together is equal to the sine of theta. Dun, 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 dun. So I'm just going to plug that in. And I find that I get the magnitude of the cross product divided by each of the individual magnitudes of the vectors is equal to the height. And we can see that the magnitude of v cancels with the magnitude of v. So we found out that the magnitude of the cross product times w is equal to the height. So going back to our original equation, what is our area of our parallelogram? It's the magnitude of w, the base times the height, and we just found out what the height is. So it's going to be the base times the magnitude of v crossed with the magnitude of w, all divided by the magnitude of w. Ooh, check this out. My magnitudes cancel again, and I find out that the area of a parallelogram is exactly equal to the magnitude of v crossed with w. Dun, 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 dun. That's our big conclusion, our big application of cross products, finding the area of the parallelogram spanned by both v and w. All application we aren't going to work through in detail. It's something that you're going to work through in your problem set. We're going to look at the volume of a parallelepiped. So parallelogram is something that you've heard before from elementary school math. Parallelepiped is probably something that you haven't heard of. So a volume of a parallelepiped is spanned by vectors u, v, and w. What does this look like? It's a three-dimensional parallelogram. So let's say that I have a vector w, I have a vector v, let's say I have some other vector u. And the parallelepiped is going to be formed, it's like a box that's been tilted. Because instead of having right angles at each of the corners, it's going to have these wonky vector angles at each of these corners. So it's this solid that's spanned by each of these vectors. And how do you go about finding the volume of the parallelepiped? I'm going to get us started with some initial steps. All that we really have to do is we have to find the area of the base. If we called this the base, we're pretending this is the base, and then we dot that with whatever the height is. The problem is, the height, like before, it might not exactly be equal to the length of v. It's actually equal to whatever is at a right angle with the base. So in general, this volume is going to be given by, is going to be the area of the base times the height. The area of the base is this parallelogram, which we already found out is the magnitude of u crossed with v. If I have these two vectors, the area of it, and actually I could be careful and use the right-hand rule. I should say that it's the absolute value of the magnitude. Oh, magnitude is always positive, so I had an interesting thought to myself that it doesn't matter which order the u and the v's get crossed in, because whether this u crossed with v points this way or v crossed with u points this way, the magnitude of that vector is always going to be a positive number. So the area of the base is always a positive number, and it's the magnitude of the cross product of those base vectors. And then the height is going to be this vector, and my hint is that the height is not exactly equal to v, but it's going to be equal to some, where you might need to use some type of projection. to find height.